Hello everyone, good morning, good afternoon, good evening, depending on where you are listening to this second webinar of ElFys, which we are proudly presenting today. My name is Mikko. I'm CEO and one of the founders of the company. And with me here is Toni, one of our founders, also a scientist. And many of you already know that what ElFys does. ElFys is providing photodiodes with sensitivity exceeding anything seen before. It is based on patented nanotechnology, our development in the company, our invention. It is already application proven by various laboratories and also by more than 80 customers in 17 countries until now, and we can customize it as needed. Some pictures of the products that we already have, and as mentioned in these slides everywhere, we are capturing every ray of light, more or less literally. All the photons are absorbed on wide band, 200 to 1000 nanometers, and wide detection angle, without sacrificing on other performance parameters on photodiodes. Meaning that with our technology, better signal-to-noise ratio can be achieved that can be used to save in light used or other form of radiation, or make smaller devices, or obtain better signal. Here is black silicon. This is why we are black and why we absorb all the photons. As you can see from the scale bar and also from the coronavirus is dropped in there for scale, the structure is characteristically on the same order of magnitude as the wavelength of light. And this results in that the photons get absorbed completely. We capture every ray of light. And with aluminum oxide passivation, we also cause an induced junction, which then collects all the charges. And here is a collection of some of our products, and especially the one in the middle bottom, the quadrant photodiode, will be the subject of more thorough analysis of Toni. And I hereby forward this device to him to continue with the show. Thank you.
Thank you. So after the introductory presentation from Mikko, let's then move on to the more detailed technical presentation of today's webinar, which is the optimization of the silicon photodiodes for near-infrared wavelengths. As a motivation, there are numerous different applications operating in the near-infrared range, including different types of LiDAR and rangefinder applications, some free space optical communication devices, some applications from the defense field, such as laser warning systems and laser targeting and guidance applications, and also some applications in the biomedical and also even in scientific field, such as the optical tweezers included on the slide. What is common to all of these applications is that typically high sensitivity is required from the photodiode to see even weak light signals and improve the accuracy of the measurement. At the same time, also the photodetection should happen at high speed so that the application or the system can react in rapid changes in the light signal. Also, what is common to all the selected applications on this slide is that many of them utilize the so-called neodymium yttrium aluminum garnet laser, which is emitting light at 1064 nanometers. And that's why that is a wavelength that we are also focusing in this webinar quite heavily. So what have we done at ElFys to answer this requirement of photodetectors with high sensitivity and speed? As Mikko already introduced, we are using our proprietary black silicon technology to eliminate all the optical losses. And as a result, the photo response of our photodetectors, as you can see on the bottom part of the screen, is nearly ideal. We have more than 99% external quantum efficiency throughout the visible, UV visible and also near-infrared spectral range. Especially in the near-infrared spectral range, that is the focus of this webinar, you can see that also there we provide quite significant improvement to the other existing state-of-the-art technologies. But also what is still evident from the graph is that after certain wavelengths, that is around 1000 nanometers, the photo response still starts to drop. And that is because of the fundamental properties of the silicon material. To have more thorough explanation for this, you can see on the right-hand side an absorption depth graph of light in silicon as a function of the wavelength. And if we look at the light at 1064 nanometers, you can see that the absorption depth in silicon is actually in the order, the depth is in the order of millimeters, while the piece of silicon that is in the detector is typically some hundreds of micrometers. So some of the light goes through the silicon wafer and the absorption is relatively weak. This leads to an obvious way how to improve the response for near-infrared, which is increasing the detector chip thickness. However, the drawback is that the detector would then become slower since there is longer distance for the carriers to diffuse or drift to the junction where the signal is collected. So there is clearly some optimization needed. And this is what we have done here. So we have simulated or calculated the response and rise time of our photodetectors as a function of the chip thickness. The simulation conditions are shown there. So we are utilizing the light at 1064 nanometers emitted by the YAG laser. We are biasing the photodetector with the 140 volt bias, so the device is fully depleted and even much more beyond. We have taken the black silicon surface optical properties into account, and the active area of the device is pretty large. It's 40 square millimeters. So with red curve, you will see the rise time, and then with the blue curve, you see the responsivity of our photodetectors. And actually, these blue dots are real measurement points from our detectors. With the thick piece of silicon, 675 micrometers, we can reach with our black silicon technology more than 0.75 amperes per watt responsivity. But however, the device is operating quite slowly, so the rise time is even close to 100 nanoseconds or at least tens of nanoseconds, which is too slow for many applications. If we are reducing the chip thickness, we see that the rise time is heavily reduced, and minimum is obtained around 150 micrometers. For smaller thicknesses, the RC time constant starts to limit the rise time because the depletion width becomes very small and the capacitance becomes large. So at 150 micrometer thickness, we reach the minimum rise time and the fastest operation, but also the response is already quite heavily dropped. So it's then a matter of optimization for the specific application, that what is the optimal condition to reach the balance between the responsivity and rise time. And for one application that we will be discussing more detail in this webinar is for that the optimum thickness is around 300 micrometers, and we can see that it is possible to reach with our black silicon technology a responsivity of 0.7 amperes per watt together with less than 15 nanoseconds rise time, which is something that hasn't been possible before. So after we have now discussed the different factors affecting the optimization of the photodetector performance for near-infrared region and what kind of optimization tasks we need to do, let's then move on to our new recently launched product, black silicon 4-quadrant detector, that we have specifically optimized for the 1064 nanometer range in the near-infrared. This is how the photodiode looks like, and let's have a look what it has eaten inside, what it consists of. In the heart of the component, we of course have the photodetector chip. The active area is divided in 4 different quadrants. The idea there is that by measuring the output current from each of these quadrants, one can get positional information on where the laser spot is hitting on this active area, and then use that for laser beam alignment. This photodetector chip is packaged in a TO can with a window that has a double-sided anti-reflection coating optimized for the 1064 nanometers, and then under this photodetector chip we have an optional heater that can be used to heat up the photodetector chip. And then all these components are packaged in a hermetically sealed packaged. Let's then have a look on the optoelectrical performance of our 4-quadrant photodetector product. On this slide, let's first focus on the external quantum efficiency and responsivity of this component. On these graphs, you will first see the data for the bare chip without the package. On the left-hand side, you see the quantum efficiency is basically overlapping with the 100% line there. So we really absorb all the photons and collect all the carriers generated by those photons. And the EQE is 100% up to 980 nanometers, and the peak response at 1010 nanometers is 0.79 amperes per watt. When this chip is packaged in the package with the coating that has the anti-reflection coating in the glass optimized for the wavelengths more than 1000 nanometers, we see that actually these two curves measured from the bare chip and the packaged chip, they perfectly overlap for the wavelengths more than 1000 nanometers. So the glass is not introducing any optical losses. And the responsivity of this packaged final component with the window at 1064 is as high as 0.64 amperes per watt, which is more than 30% improvement compared to the state-of-the-art components. An interesting property of this anti-reflection coating is also that another maximum is reached at around 575 nanometers, which means that this same package could be also utilized for applications operating in that wavelength range. I mentioned that we have also a version of this product available with the heater underneath the silicon chip. And the reason for that is that, first of all, you can, by using the heater, you can keep the silicon detector at a certain temperature, even if the outside conditions where the measurement is performed is heavily varying. The other reason is that by heating the silicon chip, the band gap of the material is reduced, and light, the absorbance of the near-infrared wavelengths is enhanced. And on the right-hand side curve, you can see the responsivity of the photodiode measured at 1064 nanometers as a function of the temperature, and you see nearly linear dependence of the temperature, and the responsivity is enhanced. Of course, the drawback of the heating of the chip is that the dark current also increases. For our component, the factor is around 1.11 per degree Celsius. So there is always some optimization between the responsivity and the noise to obtain the highest signal-to-noise ratio. So the maximum operating temperature for the component is not necessarily providing you the highest signal-to-noise ratio. As discussed, also the speed of the detection is very important, and on this slide we'll focus on the rise time and fall time of our component. In this measurement, we are illuminating one of the quadrants. In this specific case, it's the quadrant number 2. For the illumination, we are using a laser diode at 1064 nanometers and measuring the current from all of the quadrants. Again, the reverse bias is the same operating voltage of 1040 volts, and we are measuring the voltage over a 50 ohm load resistance. On the left-hand side, you will see the signal with red measured from this illuminated quadrant, and then with the other colors, you see the current measured from the other quadrants that are not illuminated. And the time point 0 is in the middle, where the light is turned on, and you see that the signal of this quadrant 2 raises up quite fast, actually in 12 nanoseconds, so the rise time is 12 nanoseconds. And also on the right-hand side, you see the fall time, so when the light is turned off, the signal pulse also goes down fast, and fall time is measured to be 12 nanoseconds. The signal for the other quadrants remains essentially unchanged, which is of course a good thing. You may also notice a small peak in the signal coming from the other quadrants when the light is turned on or off, and that is because of the capacitor coupling from the other quadrants when there are some changes in the current of this caused by the illumination. But please note that the axis for these other currents is completely different. So for the red curve that is illuminated, the axis is hundreds of millivolts, while for the others it's only some millivolts. Since this detector is used for positional information sensing, of course the uniformity of the response is very important, and what the crosstalk, so we should not get signal from those quadrants that are not illuminated. So we have measured the reflection of the black silicon surface over the whole active area of this component at the wavelength of 984 nanometers in the near-infrared range, and the reflection is 0.8% plus minus 0.2%. So we are well below 1% reflection, and the reflection is also uniform throughout the whole large active area of the component. This then also transfers to uniform current measured from the photodiode. This is done at 1064 nanometers under the same 140 volts reverse bias. So the typical number for the response uniformity throughout this whole detector is 0.9%, and the crosstalk is around 1%. And here note that the uniformity is defined as the maximum current minus the minimum current measured from the small point in the photodiode active area divided by the average current measured from the component. Here you can see even more detailed mapping of this output current of the diode when the single points are illuminated. So you can see that actually it's the fourth innermost curve that shows the 1% deviation from the average. So it's really at the edge of the active area where we go out from 1% uniformity, and actually there part of the light pulse is already falling out of the detector, which is causing the change in the signal. These requirements, they already fulfill the requirements set for a reference standard photodetector set by the National Institute of Standards and Technology. Okay, so as an application example, we have selected one example from the defense field. It's the guided munition. And how this application works is that we have some enemy target, enemy tank for instance, there in the battlefield, and we want to guide the missile or bomb accurately to that target. So we have an operator there in the battlefield having a designator tool that has this YAG laser emitting the light at 1064 nanometers. And the operator uses this device to paint or shoot this target with this laser. And then the reflected light from this enemy target is detected by this 4-quadrant detector that is sitting at the nose of the missile or bomb. And a lens system in front of this quadrant detector then focuses the reflected light as a laser spot, and from the location of the spot on this quadrant detector, the missile or bomb knows how to adjust its flight path so that the ammunition is accurately hitting the target. And by our improved sensitivity in our 4-quadrant detector product, based on our calculations, the missile lock-on distance, so the distance at which the missile or bomb can lock into target and find the target accurately and land there, this distance can be increased by up to 30% compared to any state-of-the-art technologies available at the market. And what is even more, with our technology, the weapon systems becomes more reliable and robust against some disturbances there may be in the air, which is quite typical in the battlefield, that there are some smoke or dust or sandstorm or something in the air that is weakening the signal that arrives in the photodetector chip. As a final summary, I have collected here a snippet from the datasheet of the component showing the electro-optical characteristics of our detector. The main highlight is, of course, the responsivity, typically 0.64 amperes per watt. That is more than 30% higher than any existing solution can offer. Other points maybe from here is that the component that we currently have available for sales has an active area of 38.5 square millimeters per element. So the active diameter of the component is 14 millimeters. But we are also we can launch new products for different sizes according to the customer demand. The dark current level is very similar or even slightly better than the competing devices, so the increased responsivity then directly translates to improved sensitivity of the detection. And the full datasheet is available from our web pages. with that, I would like to thank you for your attendance, and I can see that we have already got some questions in the chat box, but you are feel free to raise more questions, and we are here with Mikko to answer your questions. Okay, so there is first question that can ElFys design custom packaging solutions based on specific application requirements? Yes, sure. We are quite flexible, providing custom solutions, and yes, we can definitely do that. So please just contact us and let's discuss the requirements, what you have, and let's find the best solution for you.
Yeah, and then there is the question from Kate. Are there plans to use black silicon in array detectors such as CCD or CMOS? And the answer to this is yes also. We have done ourselves like photodiode arrays, simply having multiple photodiodes in an array format. But we have also demonstrated the applicability of this black silicon to CMOS sensors such that already made CMOS sensor has been converted black afterwards, improving the quantum efficiency and even more notably reducing the noise level, meaning that the low light visibility conditions can be improved quite a lot.
Okay, then there is a question from Juhani that what are the specific performance metrics of the NIR-optimized 4-quadrant detector compared to traditional silicon photodiodes? I think I may have already answered this on the last slide. If I don't know, is it
working backwards
visible or not there? But so basically, of course, the main difference, as stated, is the high responsivity with black silicon. So this is something that clearly differentiates us from the competition. With black silicon. We basically eliminate all the optical losses. Reflection is less than 1%, yeah, that's the difference for the black silicon compared to traditional. Then if the question was for that what is the difference between 4-quadrant sensor and traditional sensor, so of course the 4-quadrant is meant for the positional information. So how this device is used is that instead of the typical one output current that you are measuring from a single pixel detector, with the 4-quadrant detector you are measuring 4 different anode currents, and by comparing those currents you get information that how much the laser spot is deviating from the diode center in the X and Y directions, and then you can align your beam accordingly so that you get the same signal level from all the pixels. Then you know that the light beam is hitting the center of the device.
Exactly, and I guess that also answers basically the next question also. And just we didn't put competitor data here because we don't think it is fair, but typically the responses are 0.4 to 0.48, and we are not sacrificing on other parameters, meaning, as Toni has a couple of times mentioned, that this all is converted to higher signal-to-noise ratio. Then there's a question about are bare photodiode chips available for customers who prefer in-house packaging, and the answer is simply yes. Please just ask. I skipped one, seems to be there is a development. Is there development kit available, compressor included? We can provide. We have installed these photodiodes into relatively large printed circuit boards for easy access and soldering on your desktop, laboratory, whatever. The compressor question is not fully understood. Further questions, or Toni's presentation was quite exhaustive and concluded and contained everything. That's Henrik.
Okay, so there is a question from Henrik that is it possible to design and assemble black silicon CMOS on wafer level, meaning packaging black silicon wafer with other passive optical wafer stack? So is it meaning that putting some optical materials on top of the black silicon? or how do you get it?
I guess something like that. But maybe on a general level, yes, like if this means wafer bonding on for example, glass wafers or silicon wafers with three-dimensional structures or something, yeah, that sounds interesting. And I'd suggest you send an email to one of us, either me or Toni, and we can start discussing about it.
Okay, there is question from Lisbeth that what doping levels, for instance, phosphorus or boron concentration, are used in the black silicon structure to enhance the near-infrared absorption beyond 1000 nanometers, and how does this affect the depletion region with compared to standard pin photodiodes? As I mentioned something about the optimization of the performance for wavelengths beyond 1000 nanometers. One is it's the absorbance of the light in the silicon material is mainly what is affecting the performance. And so what black silicon essentially does is that it scatters the light, and the optical path length of the light in silicon is enhanced, and that is the main reason how we can improve the near-infrared absorption with the black silicon. Of course, the elimination of the reflection is also playing a big part of that. But I would answer this way.
Okay, and there was a continuation from Henrik, clarifying that it was the question about wafer bonding, and actually you see this video rolling there, that's kind of animation of how the black silicon is done. You see that black silicon is done by etching from the original surface, so meaning that these black surfaces are below the purple surfaces in this picture. And that means that these flat areas are kind of available for wafer bonding. And this black silicon is kind of protected in their cavities. But certainly there are lots of things that we'd need to discuss before going into any experimental.
Have you measured QE at 1200 nanometers? Yes, we have. I don't have a number to give out of my head right now. Of course, the performance, as you see from the graph, it drops. So the longer the wavelength, the lower the quantum efficiency is, because the absorbance is lower. I think at 1200 it's not too high anymore. We may have some chances to see some light, but please contact us if you are interested. We can provide you more data on that. We have measured that, yes.
Yeah, and this kind of gives a chance to mention that we have also done the same magic, the same black silicon magic, especially Toni here, with germanium. And with that we can achieve very high quantum efficiencies also there. But of course, many properties are rather different than with silicon. Okay, it seems like we have done with the questions and answers, and it's time to conclude this webinar. Thank you very much for your attendance, and please send us questions, send us inquiries. We are happy to discuss further, and please also join us for our next webinars and follow us on LinkedIn and other media. Thank you very much.
Thank you.